Hello everyone, welcome back to lecture series on aerospace propulsion. So in the previous lecture, we were discussing about the intakes and what is the function of intake and what is the requirement a particular intake has to satisfy. Okay, and then what is happening across the intake and what is the problem we face, that is the flow separation or stall of your intake, and what is the consequence of this stall. Okay, and then later we have discussed about the Pitot type intake. So in the Pitot type intake, we have seen the three types of intake and where exactly we use a particular type of intake and all we have seen. And later on, we have discussed about the different operation modes of an subsonic intake. Okay, so that is during the ground, that is during your static flight operation, how does that Pitot intake performs, and when we start climbing, how does that time your intake performs, and when you fly at the cruise speed or design Mach number, how do they behave, and then when you overspeed your aircraft, how do they behave and all we have seen. Okay, so in this today's lecture, what we are going to discuss about is that we are going to see about the supersonic intake. Since we have already discussed about the subsonic intake, so for your fighter aircrafts and all, we are using the supersonic intake. So in this today's class, we are going to see about the supersonic intake. How do they differ from the subsonic intake, and what are the different types of supersonic intake, and what is the problem we have when we are designing a supersonic intake, and different modes of operation of an supersonic intake. That's what we are going to discuss in this today's lecture. So let's start with the supersonic intake and how do they differ from the subsonic intake. Okay, so when we take a supersonic intake, as your name suggests, basically it is an intake which is used for a supersonic aircraft. Okay, supersonic aircraft means since your fighter aircrafts and all, they are supersonic, right? So how does the complexity of designing the supersonic intake increases as compared to the top subsonic intake is that your subsonic intake has to fly only in the subsonic region, that is during the static, that is ground operation, during your climbing, during your cruise, right? So whatever it is, basically your Mach number regime is within the subsonic. But when you take a supersonic intake, what happens is that this supersonic intake has to perform better in static during your stationary flight, during your subsonic cruise, okay, sorry, subsonic climbing, and during your supersonic cruise. Okay, so since there is a variation of Mach number regime is being increased, simultaneously the design or complexity in design of your supersonic intake also increases. Okay, so and one more issue is that whenever we have this supersonic intake, the shock waves will come into picture. Okay, so you know what is shock wave, right? Basically, it is the compression front formed in the supersonic flow across which your flow property jumps. In sense, there is going to be a rapid increase in your rapid variation in your flow property. Okay, that is what we call it as the and shock wave. So when this shock wave forms is that whenever your flow is supersonic and if there is an obstacle present in that supersonic flow, you will have the formation of this shock wave. Okay, so since the shock wave is forming, our flight is supersonic. Obviously, there is going to be a formation of shock wave in the supersonic intake. Now, you could ask, why do we bother about even if the shock wave is forming in sense? The process across your shock wave is a non-isentropic process, or entropy of your process will be increasing rapidly. So, meaning is that entropy is increasing rapidly means the loss happening across your shock is very, very high. As you know, one of the basic requirement of any intake is that it has to decelerate your incoming flow to the required Mach number with the least amount of total pressure loss. Your loss in P naught should be very, very less. Okay, but when you go for a supersonic intake, like in addition to the flow separation as well as frictional loss, the formation of waves also will contribute to a certain amount of loss. Okay, so obviously it is very, very important to properly design your supersonic intake so that it can produce a weakest form of shock wave Okay, so the shock wave is weak means when the flow is crossing that particular shock wave, what is going to happen is that the amount of loss in your total pressure is going to be very, very less. That's why I said the design of your supersonic intake is much more complicated and difficult than your subsonic intake. Okay, so how does this deceleration or diffusion happens across your supersonic intake is that since your flow is supersonic, the deceleration first mainly will occur through a series of shock waves. Okay, and series of shock wave, and through that shock wave, your flow will be the supersonic Mach number will be reduced to high subsonic. This high subsonic Mach number will be further reduced to the required Mach number needed for your compressor when it is passing through the divergence section of your intake. Okay, that's how. So in your subsonic intake, your flow will be directly decelerated because since incoming flow is subsonic, when the flow is entering the divergence section, what will happen? It will automatically decelerate. Whereas in your supersonic flow, when a supersonic flow directly enters your divergence section, what will happen? Rather than deceleration, acceleration will occur. So before your flow enters the divergence section, what you have to do is that we have to decrease the supersonic Mach number to subsonic Mach number. How do we decrease is that by means of the forming or situating or locating a shock wave of a different strength, okay, at the required location. So when the flow is passing through your shock wave, basically your shock wave is a compression wave. Compression wave means the process, that is pressure, will be increased. Pressure increase means obviously in any process pressure increase means your velocity will decrease. So the Mach number will be reduced from supersonic to subsonic when they are passing through the a series of shock wave. So in the shock wave also we are going to see different types of shock wave, oblique shock wave and normal shock wave. So irrespective of whatever the intake it is, okay, so you need to have both oblique shock wave as well as the normal shock wave if you want to convert an high supersonic Mach number to the subsonic flow. So how or why we need the both oblique shock wave and normal shock wave, we are going to see in the next section. Okay, so before seeing this shock wave, let us see the different types of intake or supersonic intake. Okay, so based on where exactly the compression process or the deceleration process occurs in an intake, we have three types of supersonic intake. One is an internal compression, external compression, and mixed compression. Okay, so what is this internal compression intake or what is this internal compression inlet is that basically the compression process will occur inside your intake. That's what mean by an internal compression inlet. Okay, so as I previously said, in your supersonic intake, you will have the formation of series of shock waves. Okay, so that is you will have the formation of oblique shock wave and normal shock wave. Okay, so you see when I'm going to have some object in my supersonic flow, I will have a shock wave formation. Okay, so if I'm going to take this convergent, you see what is this? Basically, it is a convergent divergent section. Convergent divergent section you might have here like convergent divergent nozzle, but here also we have same convergent divergent section, but still it is acting as a intake. Sorry, that is diffuser rather than nozzle. How we are going to see. Okay, so you see here. So as I said previously, internal compression intake means your shock wave as well as the entire compression process or deceleration process will occur within your intake rather than outside. Okay, so here the purpose of this intake is to the purpose of this shock wave is to decelerate your flow. Okay, so there are two types of shock wave. One is an oblique shock, another one is the normal shock. Okay, so what is this normal shock and what is this oblique shock is the basically uh, a shock wave with shock angle less than 90 degree, what we call it as the oblique shock wave. Suppose this is your flow. If you're having a shock wave your beta, the angle between your flow and your what to say, shock wave, that is what we call it as the shock angle. If this beta is less than 90 degree, what we call it as the oblique shock wave. If it is equal to 90 degree, that's what we call it as the normal shock wave. Basically, a shock wave which is forming perpendicular to your flow. That's what we call it as the normal shock wave. So you won't have a shock wave which is having a shock angle more than 90 degrees. So you could say the normal shock is the basically the strongest form of your shock wave for the given Mach number. Okay, so here, why do I have the series of this shock wave rather than I have a direct single shock wave system? Why do I have the multiple number of shock waves? Is that one thing you have to know is that when the flow is crossing a shock wave, your Mach number, if it is M1, if it is M2, your M2 is going to be always less than M1. Okay, the difference between your oblique shock wave and normal shock wave is that in the oblique shock wave, when the supersonic flow is passing through it, your Mach number will be reduced, but your M1 as well as M2 will be greater than 1. So first of all, M1 should be greater than 1, then only you will have supersonic flow, then only you will have the shock wave formation. So M2 will be greater than 1. There will be deceleration from supersonic, but the deceleration will be from supersonic to supersonic only. The Mach number will be reduced, but it won't go to subsonic. But when you take a normal shock wave, irrespective of whatever the Mach number, when the flow is crossing a normal shock wave, what will happen? You will have subsonic flow. Your flow will become completely subsonic. That is the fundamental difference between oblique shock wave and normal shock wave. Okay, so as I said previously, if I want to like decelerate my flow, you could say, why I have to use this series of in shock wave, oblique shock wave? Why can't I use a single normal shock wave? Is that if you take this location, okay, in that location, the strength of your shock wave, any location in your flow field, the strength of your shock wave is basically one of your main function is Mach number. Higher the Mach number, higher the strength of your shock wave. Okay, so why do we use this series of oblique shock wave? Is that from high supersonic to, once again I'll decelerate. Okay, I'll form some shock wave, so it will be reduced when the flow is crossing, your Mach number will be reduced. So once again I'll have one more shock wave. Like that, I'll be slowly decreasing my Mach number rather than directly reducing my Mach number 5 to Mach number 0.5. Because if I'm going to have a normal shock wave here, your flow will become completely subsonic, so it will be decelerated. Problem is that the shock wave forming, normal shock wave forming at the highest Mach number location, what will happen? It will have a strongest strength. So when the flow is crossing, the loss in the total pressure will be very, very high. So in order to reduce this loss, what we do is that we first generate a series of oblique shock wave. When the flow is crossing through this series of oblique shock wave, it will be decelerated slowly. At the end of this oblique shock wave, we will have the formation of normal shock wave. The formation of normal shock wave will be at the location where your Mach number is slightly greater than 1. If it is slightly greater than 1, say for example 1.1 or 1.01 Mach number, when the normal shock wave is forming, it will have the like weakest strength. So that means when the flow is crossing that normal shock wave, the loss in the total pressure will be very, very less. That is why, so after your flow becomes subsonic, basically it is a divergence section. So since your flow is subsonic, flow entering divergence section, it will be further decelerated. It will reach the Mach number required. So Mach number required, we have seen Mach number 0.4 to 0.7. This is the range of inlet Mach number to your compressor. Depends on the compressor, we will vary this Mach number range. Okay, so from high subsonic to low subsonic will be done when the flow is passing through this divergence section. Okay, so what is this internal compression inlet? In sense, the shock wave and the diffusion process happening entirely within this intake, what we call it as the internal compression intake. Okay, so one thing you have to remember is that the normal shock wave location should be at the location where your M is slightly greater than 1, so that the loss in your total pressure P naught will be very, very less. If you're having at the start of your intake itself, what is going to happen? Your Mach number is very high. Okay, so when the Mach number is very high, the shock wave, normal shock forming there is going to be very strongest form. So when it is crossing, your total pressure loss will be very, very high. Okay. So next one is external compression intake. So what is the meaning of external compression intake is that if the entire shock system is outside of your engine inlet, means that's what we call it as the external compression intake. Okay, so previously you have seen entire shock wave is present inside your intake, whereas in the external compression intake, entire shock wave will be outside of your intake. Okay, so here how does this compression is happening? Similar to that of previous case. Rather than having a pit out type intake, we will have a spike. When the spike is present in a supersonic flow, you will have the oblique shock wave formation. Okay, so this oblique shock wave, the spike will be designed such a way that the oblique shock wave will be exactly falling on the lip of your intake, which will reflect and form a normal shock wave. Okay, so what will happen here is that here when the flow is crossing this oblique shock wave, your Mach number will be reduced. So here we have a single shock system. Instead of that, sometime you will have the multiple number of oblique shock wave. Say for example, if I'm having a like this kind of intake, you will have the shock wave at a different location. So as your flow is crossing this multiple number of shock wave, what will happen? Your Mach number will be reduced. When it is reaching this inlet, like a lip, okay, what will happen? Your Mach number will be slightly greater than 1. So when it is passing through your normal shock wave, what will happen? It will be decelerated to subsonic, and this is basically a divergent section. Divergent section means obviously your subsonic flow entering the divergent section will be decelerated. So as such, the Mach number when it is reaching your compressor, it will reach the required value. Okay, so in this external compression intake, you might have seen this external compression intake in the ramjet engine, especially in the SR71, that is blackboard. You might have seen the ramjet engine. In that ramjet engine, you might have seen this spike protruding outside of your engine. Okay, so that spike is to produce the oblique shock wave or series of oblique shock waves, so that your high supersonic will be slowly reduced to low supersonic, and when it is passing through the normal shock wave, it will become subsonic. So irrespective of internal compression or external compression, okay, the initial deceleration is done by number of oblique shock wave and followed by a normal shock wave. So the presence of normal shock is must, then only you can have the transformation of your supersonic flow to subsonic flow. That you have to remember. Without normal shock wave, you can't reduce your supersonic Mach number to subsonic Mach number. So the presence of normal shock is must, and where exactly we are forming this normal shock also must. So it should form at the location where your Mach number is slightly greater than 1. Then only you will have the least amount of total pressure loss. So next one is the mixed compression intake. So what is this mixed compression intake? Is basically it's kind of combination of external as well as internal compression. That is, the shock wave will be present outside of your intake as well as inside of your intake. That is what we call it as the mixed compression intake. So where do we use this mixed compression intake? Is that for the flights which is having Mach number more than 2.5, we use this mixed compression intake. Okay, so once again, this mixed compression intake also, the process is similar in sense you will have the series of oblique shock wave formation followed by a normal shock wave. Okay, the Mach number will be reduced when it is passing through your oblique shock wave, and it will become subsonic when it is finally passing through your normal shock wave. Okay, so after that, once again the pressure is same, the subsonic flow entering the divergence section, it will be further decelerated to the required value needed by your compressor. Okay, so irrespective of mixed compression, external compression, or internal compression, the process is kind of same. You will have shock waves, that is oblique shock wave, series of oblique shock wave followed by a normal shock wave. Okay, so only difference is that where do we have this shock? Since if it is outside, completely outside, that is external compression. If it is completely inside, that is internal compression. If the shock wave is like on the both internal as well as external like a location of your intake means, that's what we call as the mixed compression. Okay, so next we are going to see the modes of operation of an supersonic intake. Okay, so what is this modes of operation of supersonic intake? And say for example, let us take a external compression intake. Okay, so external compression intake instance, your shock wave will be completely forming outside of your engine. Okay, so I'm going to take whatever the modes of operation we are discussing is only for a external compression intake. Okay, so what are these modes of operation in sense? Just like we have seen for the subsonic intake, where how do they behave under um, static condition? How do they behave during the climbing? How do they behave during the cruise? How do they behave during the high speed? Similarly, here, what happens if the Mach number of your flight is equal to the design value? If it is less than design value, what will happen? If it is greater than design value, what will happen? That is what we are going to see in this modes of operation of supersonic intake. Here, this is only for applicable for supersonic intake. Okay, so there are three modes of operations. One is subcritical, critical, and supercritical operations. Okay, so what is the subcritical operation, and when the subcritical operation mode of supersonic intake happens is that if the design value, that is if the flight Mach number is less than the design value. Design value in sense, for example, I have an aircraft, say we say aircraft which is flying at Mach 2. What is the meaning of this Mach 2? Doesn't mean that that aircraft is not capable of flying more than Mach number 2 or less than Mach number 2. So this Mach number 2 is the design value, or if I fly my flight at this Mach number 2, okay, the performance of my components will be like what to say, more efficient. Okay, that's what we call it as a design Mach number, or for that Mach number only your aircraft is being designed, it will operate efficiently. So what is this subcritical operation in sense? Say I have an aircraft which is having Mach number like design Mach number is 2. Okay, so before reaching this design Mach number 2, it has to fly from 0 to subsonic, subsonic to supersonic, from Mach number greater than 1 to 2. Within this Mach number 1 to 2 range, if your aircraft is going to fly, obviously that's what we call it as the subcritical operation. Okay, subcritical in sense, the flight Mach number is less than, obviously your aircraft, if it has to reach the Mach number 2, first it has to go through this subcritical mode of operation. So, or due to certain reasons, you may fly your aircraft less than your design speed. So, what will happen if I'm going to fly my aircraft less than the design speed? Okay, that's what we are going to see. Okay, so when I fly my aircraft less than my design speed, what is going to happen is that we have stated you will have the multiple number of oblique shock wave formation at the end. For the external compression intake, at the lip of your intake, a normal shock wave should form, right, in this location. So when it is passing through, it becomes purely completely subsonic. Flow entering this divergence, and you see the AI is increasing, your flow will be decelerated. But here in the subcritical mode, what is going to happen is that rather than the normal shock wave forming at the lip, it is going to form ahead of your lip. Okay, so because of this ahead of your lip, what is going to happen is that instead of flow completely entering inside your intake, some of the flow will be passing over your cowl. So what is going to happen is that because of the external flow, or what we call it as is a spillage in sense, rather than the flow passing through your normal shock wave completely entering your intake, some portion will be passing over your intake. Okay, so that's what we call it as the spillage. What is going to happen is that because of this spillage, okay, the drag will be increased. The drag, what we call it as the spillage drag. Okay, so when I am operating my aircraft less than the design Mach number, the normal shock wave is forming outside of your cowl lip, which results in spillage of your flow, and the spillage of your flow will create a drag, additional drag, the drag what we call as the spillage drag. So this is what happens, or the drag will be increased if I'm going to operate my aircraft less than the design speed. That's what we call it as the subcritical mode of operation. Okay. Next one is the supercritical mode. So what is the meaning of supercritical mode is that if my flight Mach number is greater than design Mach number, say my aircraft is designed for Mach number 2, doesn't mean that it is not capable of flying Mach number 2.1 or Mach number 2.2. As long as you produce the increased interest, it is capable. Okay, but the efficiency will be reduced. So sometime, say for example, during your mission, because of your mission requirement, or when you are combating or when you are escaping, they will not bother about the efficiency. They will like what to say, try to fly as much as possible Mach number. So what is going to happen that time? Your Mach number of your flight is going to be more than your design Mach number. So what happens when I am going to have the Mach number more than design Mach number is that the shock wave will be pushed inside your intake. Okay, pushed inside your intake. In sense, for example, here you are having a oblique shock wave. Here your shock wave is supposed to form. So when the flow is crossing, it will become subsonic. After that, it will be decelerated. But when the Mach number is increased, the shock wave, rather than forming exactly at the lip, it will be pushed inside. When it is pushed inside, means what is going to happen? Here your area is increased. A supersonic flow is entering, means once again your flow Mach number will be increased. Okay, so what will happen? The shock wave will form at the location where your Mach number is high. So what is the consequence of that? The P naught loss will be increased. The loss in P naught is increased means basically the efficiency of your intake will be reduced. So what is going to happen when the aircraft is going to fly at the Mach number more than design Mach number? What is going to happen is that the shock wave will be forming inside your intake where your Mach number is very high. Because of that, the loss in total pressure will be increased, so which will reduce the pressure recovery factor of your intake. Obviously, that is going to reduce the efficiency of your intake. Okay. Now, what is this critical design mode? Mode of operation instance. Basically, if my flight Mach number is equal to design Mach number, that is what we call it as the critical mode. So during this critical mode of operation, the normal shock wave will form exactly at the lip of your intake. So the flow, whatever the flow, will be completely entering. So you won't have any spillage, and the normal shock wave also will form at the location where your Mach number is least. So during a critical mode operation only, the pressure recovery factor for your intake is going to be maximum. That is especially for the supersonic intake. What is pressure recovery factor? P02 by P01. P01 is the total pressure of your flow. P02 is the at the exit of your intake, what is your total pressure? The ratio we should get maximum is 1, P02 by P01, but that's not possible. It will be always less than 1. So this pressure recovery factor for your critical mode of operation will be maximum among these subcritical, supercritical, and the critical mode of operation. Okay, so this is what happens. So here you won't have the spillage drag. So the spillage will occur during your will occur during your um, subcritical mode of operation. Supercritical mode of operation will result in increased total pressure loss. Whereas during a critical mode of operation, you won't have either spillage or you won't have the increased total pressure loss. Okay. So this is what all about the modes of operation of supersonic intake. Okay. So with this, whatever topic I'm just planning on covering is over. So what is that we have discussed today? We have seen about the um, supersonic intake. How does the complexity of designing a supersonic intake is being increased? And we have seen why do we need a series of shockwave in a supersonic intake, and why this series of shockwave should consist of oblique shockwave last followed by a normal shockwave. And we have seen a normal shockwave should form at the location where your Mach number is less than 1, slightly greater than 1. And then we have seen the different types of supersonic intake: internal compression intake, external compression intake, and mixed compression intake. So this name is basically based on where exactly we have the shockwave. If it is shockwave is completely outside of your intake, that is external compression intake. If it is inside the intake, that is internal compression intake. If it is outside as well as inside, that is what we call it as the mixed compression intake. Okay. So irrespective of this intake, we add series of oblique shockwave followed by a normal shockwave. And then we have discussed about the operational modes of supersonic intake for a external compression intake. Okay, so in this we have seen a subcritical, supercritical, and a critical mode of operation. During a subcritical operation means your flight Mach number is less than the design Mach number. The normal shockwave will form outside of your lip, okay, which will create the spillage and increase the drag. And during a supercritical operation, the normal shockwave will form inside your intake where Mach number is very high, which will result in reduced pressure recovery factor. At last, the critical mode of operation, basically it is the what to say, optimum mode. Okay, where your design Mach number is equal to your flight Mach number. Okay, so during this critical mode of operation, you won't have this spillage. Shockwave will form exactly at the lip. Okay, so this is what we have discussed in today's class. With this, I'll complete this lecture. So whatever we have discussed in this, actually basically I have referred from this particular textbook, that is Mechanics and Thermodynamics of Propulsion by Hill and Peters.
Like, share, and subscribe. Hit the bell icon for more updates.